invitation. This is very nice to have this workshop in honor of Ray. The title of the talk is, I guess, Arithmetic PDEs. And the plan is, I'm going to say a little bit of the motivation. Then I'm going to say a few words about Arithmetic ODEs. That's an older stuff that I did. And then some new stuff about Arithmetic PDEs. That's joint work with Lance Miller. It's in progress. I mean, there is a, it's actually, part of it is on the archive now. And we're still working on a sequel to that. The whole idea is that on Z, there are no derivations, of course. So, but you still want an arithmetic analog of derivations. And what one can propose is to take a prime P and define the operator from Z to Z as follows. So delta of an integer is the Fermat quotient. And the idea is to try to create a theory that has this as an analog of a derivation, and to apply this theory to the Diophantine questions. So, and this can be done. This leads to an arithmetic ODE theory. And there were applications that I could get. My original motivation was to try to give another proof of the Mordell conjecture. That didn't work. But there were many other applications. One of the first one was I found a different proof of the Manin-Mumford conjecture. I found applications to modular forms and other things. I'm not going to talk about these applications in this talk. I'm just going to indicate the main ideas that lead to this theory. But what is the motivation? So maybe I should start with the motivation. So the main motivation comes from the theorem that's due to Manin. It's an old theorem of his. He had a theorem about abelian varieties, but I'm going to just state it for elliptic curves. So this is the abelian variety version of this theorem was what allowed him to prove the Mordell conjecture of function fields. Let's just take as an example, this is not the most general case. Let's take K this function field and E an elliptic curve. The statement is that there exists a non-zero homomorphism. Nowadays, people call it Manin map from the points of the elliptic curve into K, which is given by as follows. So psi of a point with coordinates to rational functions is a fixed rational function of t these coordinates of the point on the elliptic curve and their derivatives up to order 2. So y double prime and y prime are in principle, you can, they're missing, but I want to write all of them. So x prime is the derivative and x double prime is the second derivative. There's one more part of the statement, namely that the kernel is the torsion group. Oops, sorry. E of k torsion. And this was used to prove the abelian variety analog of this was part of the proof of Manin's Mordell conjecture of function fields, Mordell conjecture over function fields. So this was the starting motivation for me, at least. What one can do, and this is older work of mine, is to replace the function field by a p-adic ring. So I'm going to take R to be the ZP, the p-adic numbers, maximum unramified extension, and complete it. And this ring has a Frobenius lift. This is the identity on the p-adic numbers, of course, and hence on the integers. And one can take this operator as a substitute for the derivation. Delta x is phi of x over minus x to the p over p. Of course, this is the Fermat quotient on R. And the idea is to create, as I said, a theory around the idea that this should be viewed as an analog derivation. Of course, it's not additive and does not satisfy the Leibniz rule, but it does satisfy some polynomial conditions that are vaguely reminiscent of those. And then the idea is to, the theory is to create jet spaces, like in differential algebra, prolongations of algebraic varieties. So for instance, if x is a spec of R of y is a vector of variables over a vector of the ideal generated by a tuple of polynomials, then one defines jet spaces. Well, I call them arithmetic jet spaces. So arithmetic jet spaces. Some of you might have heard me talk about these things. So in the past, this is older stuff. You add some tuples of variables, you p-adically complete, you divide by the ideal generated by these tuples of polynomials. And let me tell you what, for instance, delta of one polynomial is, and then one has to iterate that, but I'm not going to explain that. This is 1 over p. It's like a Fermat quotient. You take g, you twist the coefficients by p, and you replace, so g is somebody here. And in the numerator, I want to tell you what delta g is. You replace x by x to the p plus p. I'm sorry. Replace y by y to the p plus py prime, you replace y prime by y prime to the p plus p y double prime, etc. And you subtract g to the p and you divide by p. So this is like a formal total derivative. Okay, and then the next step in the theory, I'm trying to create one more, is if X is not affine, you glue things and you get spaces for affine, for non-affine schemes. Then the next step in the theory is if you take a global function, X now is not necessarily affine, you get a function on the points of the scheme by just replacing the formal so-called p derivatives of the variables by the p derivatives of the coordinates. I call this guy a p derivative, p derivation. So you get maps like this. Let's define a notion of delta character on G, where G is a group scheme. Well, is a map of the form FR from G of R to R, which is a homomorphism of groups. And F is, as before, a global function on the jet space, Arth jet space of X. And here is an old theorem of mine that this is in 95. That is a generalization of, not a generalization, an arithmetic analog of Manin's theorem. I had a theorem for a billion schemes, but here I'm just gonna state it for an elliptic curve to make it simple. An elliptic curve. And let's say that's without complex multiplication. There is a theorem for complex multiplication as well. Then there exists, and it's unique up to a scalar, a delta character of order 2. Order 2. The order is this R here, of order 2, psi from E of R to E of R, to R, sorry, such that the kernel, this is an analog of the theorem of the kernel of Manin, is the infinitely divisible points which have to be in the kernel from 1 to infinity, colon p infinity. So the right-hand side has to be in the kernel, but the theorem is that that's exactly the kernel. The theory proceeded from here. So I'm not gonna explain much. So this had many applications. For instance, I have a paper with Manin where we study the Painlevé-6, the arithmetic analog of a Painlevé-6 equation. There's a theorem, there's a paper with Björn Poonen where we proved some finiteness results for Heegner points. So these are purely number theoretic results. There were other applications I'm not going to mention. Okay, so that's the older stuff, the arithmetic ODE stuff. And now I want to say a few words about the new work that I did with Lance, Arithmetic PDEs. Oh, I cannot. Let's try again. Arithmetic PDEs with Lance Miller. The idea is this. So for a while, I thought that this theory is inherently unramified, and it only works with one Fermat quotient. But actually, it turns out that if you go ramified, then you can implement several Fermat quotients, and very interesting things happen. So I'm going to explain what. So let pi be root of an Eisenstein polynomial with coefficients in ZP unramified, not completed. And R pi be R of pi. R is the same thing as the guy before. Then one can take several Frobenius lifts on R pi, Frobenius lifts. And one can consider the corresponding Fermat quotients defined exactly as before. Then one can consider the jet spaces of schemes over R pi, but now with several variables. So this would be the formal spectrum of something similar, R pi. And here you introduce some new variables. Mu are now words. You see, I do not assume that anybody commutes with anybody. So these are non-commutative things. And you divide by similar ideals. You have some formal schemes. These are the arithmetic jet spaces. One can define delta characters in the same way. And now there is a surprise. It's a lot of fun, actually. One of our theorems is that if E is an elliptic curve, then there exists a unique up to scalar non-zero delta character of order 1, not 2. Let's assume that there are 2 derivations. Then there is a unique character of order 1, delta character of order 1. So this is something that doesn't exist in geometry. Maybe I should say non-CM, not maybe, but definitely. And one can find a structure of delta characters of any order. In particular, for mu and nu, 2 words on the letters 1 and 2, there exists a distinguished delta character that I'm going to denote it like this. We have a description of the kernel again. Description of the kernel. This would be an analog of, arithmetic analog of the Manin theorem of the kernel. And my last statement, I'm not sure how many minutes I have.
You still have 3 minutes at least.
Okay, here is the theorem. This is a new reciprocity theorem that looks nothing like any reciprocity theorem that we know. And here it is. So let alpha and beta be two numbers here with a small absolute value. I'm not going to say exactly what. E alpha and E beta over R pi with the same reduction mod p, ordinary, and such with the logarithms of their certain parameters alpha and beta. And we take p alpha beta in E beta R pi and p beta alpha in E alpha R pi to be such that their elliptic logarithms are alpha, and similarly for beta. Then one has this curious reciprocity theorem. Let's see, psi mu beta of p alpha beta equals pi, and now you switch the words and you switch alpha and beta. This is a sort of application that is interesting in the sense that it looks like a reciprocity result, like reciprocity theorem, but it is not does not fit into other types of theories that lead to reciprocity theorems. So that's one of our applications. We have other applications to Heegner points and to modular forms, but that's where I guess I will stop. Thank you.
All right, let's thank Alex for this very nice talk. All right, do we have any questions or comments? Just go ahead and unmute yourself. All right, so one thing I was wondering, is the restriction to just finitely many operators essential for what you're doing? I was just thinking, if you think of the integers, somehow you have infinitely many primes.
This is a theory that holds prime by prime. So for each prime, you consider finitely many operators. And if you're asking about interaction between primes, that's another story. And there is an adelic version of this. Yeah. One can create an adelic version of what you see here and compare what happens at 2 primes, but we don't have reciprocity theorems for that.
So I got a question.
Yeah.
So if you do 3 of them, do you get anything new other than from the 2? Is it generated by binary relations, or do you get new things?
Yes.
With
So
3?
if, right, I understand the question. So if instead of 2 here, let's see if I can write. If instead of 2, you get 3, then you get several guys like this. Actually, the expected number with the relation between them. So the theory is works well with several guys. By several guys, I mean 1, 2, 1, 3, you know, this kind of thing. 2, 3. Yeah.
But do you get something that depends on 1, 2, and 3 that's not generated by those?
In order 1, these are the generators. No.
Yeah.
The surprise in this theorem is that you get something of order 1 that doesn't exist in the ODE case. So in some sense, the operators conspire to create objects of lower order.
And is it a formal groups computation?
This is not a formal group thing. It's more global than formal because it's these are p-adic global objects. They are not simply, they do not simply come from the formal group. But of course, the formal group has something to say and is used in this theorem.
Thanks.
Okay, if there's no other questions, comments, let's thank Alex again for his nice talk. And okay, all right.
Yeah.
If you can stop the sharing.
Yes. Yeah.